Welcome to the Explainer. We're about to shrink down, way down, to the nanoscale, to tackle a really fascinating question. Do the rules that govern our big, everyday world still apply when things get unimaginably small? Let's dive in.
So here it is, the big mystery right up front. We've got all these laws of physics and chemistry that work perfectly up here, in our world. But the nanoscale, that place is notoriously weird. So do those old, reliable rules bend, break, or, hold strong when we enter this tiny, bizarre realm? That's exactly what we're going to find out.
So we're kicking things off with what seems like a simple question, but at a ridiculously complex scale. If you take metals that we totally get in our everyday world and you shrink them down, do they still play by the same chemical rulebook?
Okay, before we actually meet our metals, we need to get on the same page about the rule that's being put to the test. It's a concept called miscibility. And honestly, it's simple. Think of it like this. Some things mix together perfectly, right? Like salt and water. Others, not so much. They absolutely refuse to, like oil and water. That tendency to either mix or not mix, that's what we're putting under the microscope.
All right, it's time to introduce the stars of our show. Now, the researchers here were clever. They didn't just pick one pair of metals. They picked two very, very different contenders to face off in this little scientific showdown.
And this is what sets up our whole experiment so perfectly. On one side, you've got platinum and silver. In the regular big world, they are completely immiscible. They're the oil and water of the metal world. But on the other side, you have palladium and silver. These two, total opposites. They're perfectly miscible. Just like salt and water, they love to mix.
And that, right there, brings us back to the heart of the matter. If we take these two pairs, with their completely opposite personalities, and we shrink them down to the nanoscale, will they stick to their old habits? Or is the weird physics of the tiny world going to force them to change their ways?
So how in the world did the scientists actually do this? How did they run this tiny test? Well, let's take a quick peek at the experiment they designed.
First off, we really have to wrap our heads around the scale we are talking about. The core particles they made were just 2 nanometers across. To put that into perspective for you, that is 50,000 times thinner than a single strand of your hair. We're talking about a truly mind-bogglingly small level here.
So what was the recipe for this whole thing? Well, in really simple terms, the scientists mixed the metal salts together in a solution. Then, and this is the cool part, they zapped it with radiation to force these incredibly tiny particles to form. Finally, they used this special technique with X-rays to see exactly how the individual atoms were arranged, basically to see if they were all mixed up or if they were keeping their distance.
And this brings us to the moment of truth. After all that work, what did they find? Did the rules of mixing and separating change down at the nanoscale? It is time for the verdict.
Let's start with our first contender, platinum-silver. Now remember, in the big world, these two absolutely refuse to mix. They are the oil and water. So, what happened when they got shrunk down? The verdict is in, and they stayed separate. That's right. Even at just 2 nanometers, the platinum and silver atoms kept to themselves. The old rule held up. The oil and water of the metal world, well, they stayed oil and water.
Okay, round 2. Now for our second case, palladium and silver. These are our salt and water metals that, in the big world, mix together perfectly to form a beautiful alloy. Did they keep up this friendly relationship at the nanoscale?
And yes, they did. The palladium and silver atoms mixed together seamlessly, even when they were formed into these tiny nanowires. So once again, the established rule held true. What they did in the big world, they did in the small world. No surprises there.
So here's the final scorecard, and it really sums it all up, doesn't it? For both metal pairs, their nanoscale behavior perfectly mirrored their behavior in the big world. The ones that don't mix stayed separate. The ones that do mix, mixed. The old rules held strong. Okay, so the rules held up. You might be thinking, all right, so why is that a big deal? Nothing new happened. But finding out that something doesn't change is actually a really, really important discovery. And here's why. You see, the crucial thing here is understanding why the platinum-silver pair stayed separate, and the researchers explain it right here. The atoms of platinum and silver are just different sizes, so trying to cram them together into one neat structure creates an incredible amount of physical strain. It's like trying to fit the wrong puzzle pieces together. And it turns out, even at the super small nanoscale, that strain is just too powerful to overcome. The atoms would rather just stay apart than deal with all that stress.
And look, knowing which rules hold strong and which ones might break is absolutely critical for the future of technology. I mean, if we want to build things at the nanoscale, and we do, things like new and better catalysts, or advanced electronic devices, or even sophisticated biosensors, we have to know the rulebook. This experiment basically confirmed a fundamental chapter in that rulebook. It gives engineers the confidence to predict how materials will act and to design amazing new things.
So, we've learned today that at least one fundamental rule of chemistry holds up, even in the extreme world of the nanoscale. And that leaves us with a pretty tantalizing final thought, doesn't it? If this rule applies, what other rules do too? And maybe even more exciting, which of the established laws of our big world are just sitting there, waiting to be broken as we venture even deeper into the tiny one?